So we are on the very last video for the Unit 7 Day 3 work on asymptotes, and we're going to talk about our third kind of asymptote, oblique asymptotes, and then do an example where we are kind of putting it all together. So oblique asymptotes happen in rational functions, and you guys will remember this, I think, from last year, where the degree of the numerator is exactly one more than the degree of the denominator. So for instance, if you had, say, an x cubed over x squared with other stuff, or x to the 6th over x to the 5th with other stuff. Obviously, if you just had those two terms, it would just simplify to be a linear function. But that's kind of the idea, that if you have a cubic over a quadratic, if you divide those out, we'll get to be closer and closer to kind of a linear function. More interesting stuff might happen with small values of x, but as x gets really, really big, the other terms don't matter so much. And what's actually going to happen is that the shape of this function will become essentially linear. And that's what our slant or oblique asymptote really is doing. So when we're looking at oblique asymptotes, it's another expression of the limit at infinity. And really it's saying that when you approach infinity, this function, it doesn't approach a numeric value or a real number like when you have a horizontal asymptote, but what it does do is it approaches a linear function. So it's approaching a line, and it will be tending off towards negative infinity or positive infinity, but it's doing that in a very particular way that it is going basically very, very close to a straight line. So what we're going to do for this is to be able to rewrite this function as with a division statement. So I'm going to do 2x squared plus 3x minus 1 divided by x plus 1. And I think most of you guys will do this with synthetic division. If you use the long division, that's fine too. So I'm going to bring down the 2, multiply these guys and put the -2 up there, add down. So I'm adding 3 plus -2 is 1, multiply these, -1, and add down, I get -2. So this is the quotient here, and this is the remainder. So I can rewrite this function as 2x plus 1 minus 2 over x plus 1. So here you can see that as you approached infinity, if you were getting really, really enormous values for x, this 2 over x plus 1 is going to get closer and closer to 0. Okay, so just to be really clear, the limit as x approaches infinity or negative infinity of 2 over x plus 1 equals 0. So as you get really, really big values of x, this part just doesn't matter. And the function is going to be essentially very close to this 2x plus 1 line. So we could graph that line and see how that function was tending towards that line. We can take another thing that we want to be able to do is to see, is it approaching this from above or below? So will this piece be a little bit above my function or a little bit below my function? So here I'm going to take a look at what this is doing if we're doing this from positive infinity or negative infinity. So I am subtracting this, and if x is going towards positive infinity, I may actually just kind of put that negative out there to be the negative sign there. So as x approaches positive infinity, this whole thing will approach 0, but from below it'll be a little bit negative because of that negative sign there. So you will be having some little addition of a negative number at the end, or subtracting something off of the end of this. So it's approaching your oblique asymptote from below. And we can look at the limit as x approaches negative infinity as well, of this -2 over x plus 1. Here, if x was a very large negative number, this would be negative on the bottom and negative on the top, so it would be a positive. So this, as you go towards negative infinity, is approaching the oblique asymptote from above. So we can kind of do a little sketch. This one doesn't ask us to graph, but just to kind of give you an idea of what the function would look like. And you can, any of these that you're struggling with or wondering how these asymptotes are working, you can always throw these into Desmos as well. It's always a good strategy to be able to get a better description. I know I'm going to have a vertical asymptote at -1, so I'm going to put that in. X equals -1. And then I'm going to draw the graph of my oblique asymptote, 2x plus 1. This is not going to be necessarily super accurate, but I have a y-intercept of 1 and a positive slope. So y equals 2x plus 1. And just like we did before, if we checked, I'll write out the limit around the vertical asymptote. So my vertical asymptote is x equals -1, and the limit as x approaches -1 from the left of f at x, and the limit as x approaches -1 from the right of f at x. So whichever way you go about this, this is going to, as you come up to -1 from the left, you're going to get big positive numbers. And as you go towards -1 from the right, you're going to get negative numbers. So if I go over to my graph to graph my function, I would see this as the behavior around that vertical asymptote, just like we did before. Now I also have kind of similar behavior about my oblique asymptote. So I'm approaching the oblique asymptote from below as we go towards positive infinity, and from above as we go towards negative infinity. So this function still, the limit of the function is still going to be infinity or negative infinity as we go towards our end behavior, but we can be more descriptive than that. If it travels along a linear path, we want to be able to describe that, because it's not just kind of randomly zooming off towards infinity, it's going towards closer